Hello. So we'll get started with the last talk of the session, last but not least. So we are very happy to have Zhang with us today. So is an associate professor at Chicago, and previously he was an associate professor at ETH Zurich. Okay, so I will give you the academic introduction first. And before that, he got his PhD from Wisconsin-Madison and did a postdoc at Stanford. So Say has won a lot of awards, from SIGMOD Best Paper Award, SIGMOD Research Highlight Award, and he has done foundational works in computer systems, networking, AI, and democratizing machine learning, and so on. And another part of Say is like he's the CTO of Together AI, and Together it seems like it's doing extremely well. So we'll hear from Say about his academic and industry journey today. So we are very happy to have you here.
Thank you so much. Hi, Aaron. Thank you for coming to my talk. Today, I'm really excited to share with you what we are doing essentially at Together and how we think about space. So here we talk about language model or foundation models, right? So, and it's very hard to imagine that not that far like ago, we actually do not have that many language models. So if you think about the Llama like as a model, it's only like a 1 year and 2 months or 3 months old, something like that, right? So that's how fast the field is actually moving. So once upon a time, there's actually no Llama. So if you look at what happened essentially back then, like almost like 2 years ago, this is the first version of Helm, right? So and yeah, so there's only like 6 open models, right? So and essentially we look at them, so they actually get released in actually 2 different groups, right? So there was this very big wave, kind of October 2021, right? So around that time. And then the second wave is around essentially the second half of 2022. So I mean, this is essentially open model space like 2 years ago, right? So and we actually run the first version of Helm. So the way we run it is we essentially get a whole bunch of like idle GPU in 4 different institutions. Whenever GPU is free, we just grab them. And essentially, we just run Helm like in that way. So if you look at Helm essentially today, right? So the community has essentially been through a really interesting process. And if you look at Helm, right? So essentially, there's an open model already essentially in the top 6, and this is before the Llama 3.1 release, right? So in the last 2 years, the community really changed the perception about what open source model can actually do, and it's only getting like start from there. So, and this is actually a pretty interesting trend, essentially in the last 10 years. If you look at the driving forces of many of the opportunities that we are having today, essentially the field has been driven by essentially 2 different driving forces. There's the data and there's essentially the compute. So this is the OpenAI scaling law paper, right? So the x-axis is actually the data set, the y-axis is essentially the loss, lower the better, right? So essentially the more data you start to push into the system, the better the model that you are going to get. But of course, right, those data will actually explode your compute, but those compute you are not actually burning for nothing. The more compute that you actually burn, magically, the lower the loss that you are going to have. So, and because of this, if you look at in the last 20 years, the evolution of the data side, right? So you can see something like this, right? So back then, right, the large data set we have as a community is essentially ImageNet, right? Like 1.3 million images. If you look at today, right, people start to put like billions of images into the training process, and it really has been looking like that in the last like at least 20 years, right? So, and on the other hand, it start to explode the computation, right? If you do GPT type of model, it's like 1,000 GPU for a month, and that's really a pretty small model in today's standard, right? So data and compute is really driving this field forward. So, but there are also kind of challenges that we are facing as a community, right? In the last 2 years, start trying to do open models. First one is there are a lot of interesting data sets that actually exist. So there's Pile, there's C4, there's Stack. But on the other hand, I don't think the open community have been figured out essentially what is the data recipe. How can we map raw data to a high quality core to actually maximize the utility of the model? How can we clean the data? How can we mix data? And how can we reproduce a recipe when the customer comes in with a new application? We have no idea how to do that. And the diversity of data is also lacking in the open space. How can we go beyond internet and code and synthetic data is there any way to actually open up the channel for open source community to access a more diverse pool of data set? So I think that's really like the really open problem that like we are facing today. And also on the computation side, so I think the community managed to get the computation resources and make really amazing projects kind of possible. But on the other hand, we are still essentially lack of compute, right? So, and the other side of it is we have a very strong requirement on what is the connectivity and the locality of compute that can be useful for training such a model. So these two actually go hands in hand, right? So like the stronger the requirement you have on your infrastructure, the smaller the competition pool that you have, and then more like that kind of contribute to the shortage of the compute itself. And also the reuse of the compute is actually like, if you look at last year, how many like 7 billion model that people have been training, right? So people kind of train like 3 or 4 different models at a very similar size. Essentially, they always train from scratch, but do not actually build on each other, right? So many of these, I think, are problems that we are facing today as a community. And many of the answers to these questions need the whole community to actually figure out. So, and together, we hope to actually stimulate it in our own way. So, and the way that we like to think about space is by thinking about this as a tension between 3 different players. On one hand, there's a data side, right? So data become larger, become more complex. The quality of data start to decrease, and the kind of amount of effort and the cost that you need to actually clean the data, acquire new data start to increase. And as a consequence of that, the models start to get larger, get more complex to essentially accommodate the complexity from the data. And both the data and the model start to essentially add pressure to the infrastructure. You start to require a huge amount of computation to actually train the model, huge amount of storage to actually serve the model. And as a reaction to that, the infrastructure start to react in kind of 2 different ways. It start to specialize, and on the other hand, it essentially start to scale out. So essentially, there's a very interesting loop here. So one way that we think about infrastructure is essentially the 3 different bets that we are making in the beginning. The first one is infrastructure will probably start to getting more and more aggregated. The way we look at it is you look at, for example, like GB200. So this is at kind of GH100, right? You start to have this very interesting memory link between CPU and GPU. And if you look at data center, right, as a computer, you start to have almost like 400 gigabytes per second bandwidth between 2 different machines. So those are very different scale of aggregation happening at 10,000 GPU level, right? So I think that's a new phenomenon that's going to continue for the years to come. And the second thing is you also start to see this geo-distributed disaggregation of infrastructure, right? So some of them are kind of because of economics, some of them are because of, I mean, you need so much power to actually put one of those things in one city, right? So, and some of them, we do need to have this geo-distributed network compute to actually serve my inference request. So there's this kind of disaggregation happening at global scale. There's the aggregation happening inside the data center. And then there's a huge impact of workload acceleration, right? If you really like, assuming GPU is like $10 per hour, if you make that thing like 1% faster, you are pretty much saving $1,000 per year, right? So people are building like 100,000 like GPU clusters like everywhere, right? So I mean, all these 3 come together, essentially how we think about the bet we are making as a company. So essentially, we want to essentially have this like acceleration-centric effort, right? So from the data to the infrastructure to the model, and try to optimize them all together and just like bring down the cost for the end customer. So essentially, on the infrastructure side, how can we think about utilization, right? So on the model side, how can we relax what we can do on the model? How can we do quantization? How can we do architecture approximation? Model give you this relaxation space, and data essentially try to close the gap of what you can do between the original model and the relaxed model. And the relaxation, right, and the data come into the infrastructure, improve the utilization, and bring down the cost. So that's essentially how we think about it. Together, we have been doing essentially these 3 different dimensions all together, right? So on the data part, we have been trying to understand data, how can we understand data recipe, and how can we map data quality to model quality in a principled, reproducible, and scalable way. And on the model side, we are very excited about essentially non-transformer architecture. How can we bring them from research to production? On the infrastructure side, we are kind of very excited about optimizing the economics. How can we do a joint optimization between systems, including the kernels, communication primitives, the architecture, right? So, and the algorithm and modern hardware, how can we really combine what we can do on the data and the model side and essentially bring down the economics? So that is what we are really passionate about. So let me just go through some of the examples that we have been doing, right? So this is one of the projects we have called Red Pajama, which is essentially on the data side, right? So it's a 30 trillion token data set. And what we are trying to do is try to provide this modular view of data quality. So if you look back like 1 year ago, right? So when Llama 1 first got released, it's a great model, but I think what's really make that really fundamentally important is that's the time the community really get hope. It's like we are actually able to have open model that is good. And the first effort that we have right after Llama release is, okay, let's try to reproduce that. So Red Pajama 1 is the data set. Essentially, we try to reproduce a Llama recipe as close as possible and try to match the token count as much as possible. So this essentially like give you this like 1.2 trillion tokens as an open data set. So that's essentially where we get started. And in the last 2 years, we are very excited to see how many people are using Red Pajama, right? Many of the model that you are using, yeah, probably many of the model you are using last year, what's trend on Red Pajama. So, and, but there are also lessons that we learn, right? So like first thing that we learn is it's very important from the data perspective to allow the user to twist the data in a flexible way. So for example, the degree of duplication, different filter criteria, different combination of the filter, right? All those kind of filters that you can actually allow the user to compose is way more important than having a single data set that can do everything, right? So that the magical data set might not exist, but being able to provide this abstraction for people to play with data, to mix it themselves is actually very, very important. So that actually inspired Red Pajama version 2. Essentially, we process all the common crowd dumps through CC9 that give you like 100 trillion tokens. And we do very basic minimum filtering and deduplication. And then essentially we overlay the data with 40 different quality signals. Some of them are from machine learning heuristics. Some of them are from rules. Some of them are, for example, Faraday deduplication signal, right? Essentially for every single token in the data set, we kind of overlay 40 different signals to really quantify essentially different perspective of quality. So, and essentially this gives you these 40 different ways to look at a single data set. And this is like, it's kind of give you this very modular view of quality, right? If you want to say, okay, I think golfer paper is a great quality filter, you can pretty much implement the whole thing like 20 lines of code. If you say, oh, I actually think C4 is great, right? So you can actually implement that in a very easy way. And what this open up is give you this abstraction to actually potentially learn how to combine all the filters to create your new data set. So it's actually give you this new dimension that you can play with. So these are actually different filter rules that you can actually implement in the data set, right? So, and this is actually, we train a whole bunch of like 500 million parameter models on different ways of filtering and mixing the data. So, and you can see, right, on different evaluation benchmark, different ways of mixing those data actually give you different quality, right? So essentially, data is very important depending on what you are going to evaluate the model for. And being able to mix the data in a flexible and modular way give you this flexibility of optimizing different applications. So, and why that's important? For multiple reasons, right? So first one, data is really the bridge to actually kind of close the gap between different architectural relaxations. If you want to do quantization, you need to have a very good data set to do calibration. If you want to do crazier approximation, which I will talk about later, you need a very good data set to actually close the gap, right? So, and essentially the quality of your data to close that gap, depending on how crazy the relaxation that you are able to do, which kind of decide the economics of the product. And second, there are a lot of optimizations that help economics, for example, spatial decoding, right? So which actually require a very careful data recipe for that whole thing to work, right? Having this understanding of data is actually very important to actually optimize the economics. So let me just give you one example, right? So this is one product we have called Stripe Hyena. So, and the fundamental question that we are curious about is, can we build an architecture that's actually not transformer, but matches the top modern transformer in quality? So that was the curiosity back then. So what we have done is something kind of interesting. So we start from a kind of original like Mistral 7B, right? So and there are multiple things we are doing that are kind of interesting. The first one is instead of having a pure non-transformer architecture, we start to mix different layers together. Essentially, here we kind of start to replace half the layer with a Hyena layer, but we kind of keep half the layer still as a tension. So it's kind of a hybrid architecture that has both transformer layer and non-transformer layer. And then we start from the original model and we add a whole bunch of distillation signal on the radial progeron data set at the layer level, right? You have the layer input, you have layer output, you try to match it at layer level. And then you try to essentially do a full next token prediction, continual pre-train over the hybrid architecture. So what's actually very interesting is after you train the whole thing on high quality data set for like 100 billion tokens, magic start to happen, right? So like at the end of the day, right, if you compare with the original model, on a whole bunch of benchmark, it's only like 2 or 3 points lower in quality than the original Mistral model, which is actually very good model. And then if you instruct and tune it for another like 10 billion tokens, you start to essentially improve the model kind of to a level that's actually better than the Mistral model. And on long context task, it's actually give you a pretty significant improvement because those like non-transformer architecture, they are actually pretty fast on long context tasks. It gave you a whole bunch of improvement there. It's actually make your system actually much faster. So this is one example when you have 128K context, you can be up to 2 times faster than the original Mistral. And this is a memory footprint. So essentially this dataset give you these ways to close the quality gap, which will allow you to do architectural approximation, which give you this improvement on the economics. So that's actually one thing that we have been super excited about. Essentially, that's why we essentially try to bridge this gap between these 3 different players. Yeah, so sorry, I have a question. So it's a kind of hybrid. So not pure. So essentially, there's 50% of the layer, actually like 30% of the layer are still transformers, and the other 70% are SSI. Yeah. So, and what's actually very, very interesting in the actual architectural design is it's kind of start to open up essentially this trade-off between pure transformer layer, which is on the left-hand side, and the pure SSM, right, which is on the right-hand side, right? So they actually have different shape in the scaling law. And what's actually interesting is this line is essentially the quality of a pure transformer architecture. The fact that they're actually points below this line means that by mixing things together, you can actually have something that's actually better than pure SSM and also pure transformer. And if you have a very good data set, you are able to train such a model that actually close the gap between this hybrid architecture and a really good original model, which is Mistral 7B. So that's essentially what we learned from this exercise. So, and yeah, I think I'm right on time. Yeah, so this is actually this one example of how to close the loop, right? We start from data, which will allow you to actually close the loop, like close the gap to a model architecture approximation, which in principle have essentially benefit on the system side, make your infrastructure much easier to build. And into the system side, actually bring down the economics and essentially lower down the cost and pass on many of the benefit to the customer. Right. So, and what gets us really excited about is keep doing this loop again, and again, and really make sure every single one and every single applications can really use foundation models at scale. So that's what we are very excited about. Yeah, thanks. Yeah, thanks to everyone for the attention. I'm happy to answer whatever question you have. Yeah. Oh yeah, so like essentially like transformer is essentially quadratic, like with respect to the context length, right? So and there are different ways for you to actually linearize it, to make that kind of linear or almost linear with respect to the context length. So hyena is essentially a more convolutional view of that. Yeah. So it's actually like linear with respect to contact length. So there are multiple architectural design. For example, like Mamba, which like TradeOS, right? So is another way of making this like attention more kind of linear. And there are actually other different like layer design. This is kind of one of that. Yeah.
So is there any integration why mixing transformer and
To be honest, we don't know. So I think that's something that many people have observed, right? If you look at like AI21, just have the Zhang model, right? So it's also kind of like a mixture of different type of layers. So I think it's, you can, I mean, to be honest, we don't know. Yeah. Part of the feeling is the transformer layer still give this like global scope, right? So which, I mean, maybe you do not need that much global scope for every single layer. Maybe that's the argument, right? So you are able to shrink some of the flops and then use them to actually pipe in more data. Maybe that's one way to think about it, but we don't know, right? But that seems to be a behavior that people keep observing. There must be something fundamental about it, but we do not know for sure. Yeah.
So I don't know if you said it or maybe I just heard it, I don't know, right? Of like making something like stat sign work actually needed like good quality data like that. So did you try it on just like file or something and it did not work so well? I mean, so like there's
Yeah.
of course your training recipe in your architecture, right? Like a layer by layer decision, all that. So keep all that fixed. But just have like, your boutique data set and maybe a less boutique, but kind of still pretty standard data set. And how much difference does the data set make?
Yeah. So I think it really depends on, so like one thing I learned, so like one biggest thing I learned after we do the company, right, after being a professor was, it actually depends on how you measure the difference. So when we write a paper, right, the thing that we measure is what is the average, what is the median, right? So if you measure that, I mean, we do a whole bunch of data mixture analysis, it probably a couple points difference, right? So that's probably on the average. After we do the company, I realized average is kind of a very mild way to measure difference. You want to measure P5, right? What is the worst 5%, right? And if you really want that thing to be bounded instead of the average, if you measure P5, oh, it's a lot, right? Because you want the data to be balanced. You want to make sure whatever the original model know, this one also knows, and whatever user come your way, right? So that requires kind of perform reasonably well, right? So I think depends on how you, like where you cut, right? Yeah.
So this is probably true for anyone, but I'm saying in the context of making Steinheiner from Mistral,
Yeah.
right? Like, what you said sounds like generically good data practice for anyone, right? So which is different from, so are the two coupled or just like completely orthogonal things that you should do both?
Yeah. So when we first started, we thought we can learn something really unique about the data recipe of doing distillation, right? For example, you do have more signal. You can do more like this, like active learning type of thing because you know the original data. You can actually kind of probe the kind of space, right? Like try to think about what is the data importance of that, right? So I still believe that's true, but we tried really hard. We cannot figure it out. Yeah. So at the end of the day, I think where we get stopped is a good recipe seem to be good enough. I think we could do better by considering the original property of the model, but we don't know how to do it. Yeah.
Then let's take other questions offline. So let's thank
Thank you.
We are now moving back again to Atkinson Hall for the student poster session, and all the students who are presenting poster, we have a dinner for you guys there.